All right, let's go ahead and get started. I want to welcome you to this fourth screencast of Unit 4 of the periodic table. We were looking at periodic trends, and we said that, for example, if you move from left to right across the periodic table, that the atomic radius size decreases. It gets smaller. If you look from top to bottom in any family or group, the atomic radius size gets bigger, and we outlined reasons for those. What we want to take a look at now is something called electronegativity, and we want to find out what the trend is, if any, for electronegativity. So first of all, what is electronegativity? Well, I'm going to draw something called a Lewis structure for a molecule that we should be fairly familiar with. It's water. In the water molecule are bonds that contain pairs of electrons. So between this hydrogen and this oxygen, for example, there are 2 electrons. Between this oxygen and this hydrogen, there are 2 other electrons. And by the way, there are what we call non-bonded pairs on that oxygen, but we won't concern ourselves with those. As it turns out, oxygen is more what we call electronegative than is hydrogen. In other words, oxygen pulls electrons from nearby atoms more tightly than hydrogen. We use the symbol for electronegativity, what I've just shown, and so we say that oxygen has a greater electronegativity. Sometimes people write like a little arrow with a kind of a tail just like that to show that just like that. So oxygen is more electronegative than hydrogen. Is there a trend? And the fact is there is. As you move from left to right across the periodic table, electronegativity increases. And as you move from top to bottom, it decreases. So another way to say that is electronegativity is increasing in this direction and it's increasing in this direction, or you can just replace those 2 arrows with a single arrow shown for increasing electronegativity. In other words, the atoms at the upper right-hand corner of the periodic table have the greatest electronegativity, the greatest tendency to attract nearby electrons. And those in the lower left-hand corner have the lowest tendency, the lowest electronegativity. All right, so what's the element that has the highest electronegativity of all? As it turns out, it's not helium. Helium, if you look at a periodic table, is the most upper and to the right, right? But it's not helium. And the reason is that noble gases don't have electronegativities. So excluding the noble gases, the element that has the highest electronegativity is going to be fluorine. So fluorine has the greatest tendency to pull electrons towards it, right? Now, the element with the lowest electronegativity, as it turns out, is francium. That's in this lower left-hand corner. Francium is the lower left-hand corner of the periodic table. So there you have it. Electronegativity increases as you move from bottom to top, left to right. Okay? All right. So that's the electronegativity trend the trend for electronegativity. Now again, the noble gases don't have electronegativities. Why? Because they have an octet of electrons in their outer shells, and they don't want to acquire more electrons than they absolutely already have. So let's take a noble gas. Let's take neon, for example. I'm going to write what's called a Lewis structure for neon. I'm going to show the electrons that are in the outermost shell. We can do it just like that. So neon already has 8 electrons. It would have no reason to want to acquire another electron. So again, noble gases do not have an electronegativity. So that's electronegativity in a nutshell. Let's look at now something called first ionization energy. What do we mean by first ionization energy? Well, first ionization energy is the energy required to remove a single electron from an atom. Okay? It's the energy required to remove an electron from an atom. Let's say, for example, sodium. If I have sodium, just like that, sodium has 11 total electrons. If I want to reduce that number by 1, I'm going to have to put in a certain amount of energy. So I'll make an arrow like this, and I'll write energy just like that. And when I do that, I'm going to get Na+, I'm going to get an ion, in other words, and then I'm going to get an electron. That energy required to remove that electron from the sodium is called the first ionization energy, and all atoms have them. It's the energy required to remove an electron from a neutral atom of an element. So first ionization energy trends follow the electronegativity trends exactly, except that noble gases do not have, or do have rather, they do have first ionization energies. As we'll learn later, they're rather large, they're rather high, but they do have first ionization energies. Let me go back and just diagram that one more time. So remember, the first ionization energy trend is going to be up and to the right, including the noble gases. Including the noble gases. Now, the noble gases have especially high ionization energies. Why? Well, because they have an octet of electrons. They really don't want an electron to be removed. They're going to resist it vigorously. They have an octet of electrons and they are already happy. They don't want to be disturbed. Okay, so that explains why the noble gases have first ionization energies. They're rather high, as we've seen before, but they don't have electronegativities. They have no desire to pull an electron from another atom. So let's get some practice in now. So to do this practice, you're going to need a periodic table. If you need to pause the video, go ahead and do that now, and make available to yourself a periodic table. So the question is, which is the larger atom? So we're going to need to think about trends of the periodic table. So which is the larger atom? Sodium or potassium? Well, let's find sodium and potassium on the periodic table. Sodium is number 11. Potassium has atomic number 19. Remember, the trend is as you go down the periodic table in any family or group, atomic radius size increases, right? It increases. So which would have the higher electronegativities? Higher atomic radius size? Well, it would be potassium, wouldn't it? Because potassium is lower, it's farther down in the family or group than is sodium. Now let's take a look at sodium and aluminum. Let's compare those two. Well, those two happen to be in the same period. Sodium and aluminum are both in period 3. But aluminum is further to the right. Now, what happens to atomic radius size as you go from left to right? Atomic radius size gets smaller, doesn't it? So that would make sodium larger than aluminum. Now, let's compare boron to oxygen. Boron is number 5, oxygen number 8. As you move down the periodic table, across the periodic table, I should say, from left to right, atomic radius size gets smaller, so boron would be the larger of those two atoms. Now, neon and krypton, both noble gases. As you move down the periodic table, the atomic radius size is going to get bigger, so krypton would be the larger atom. Calcium atom and calcium ion. All right, let's not get confused here. Calcium atom, that's number 20, versus calcium ion. Well, what happens to an ion of calcium? What happens to calcium to form calcium ion, right? It goes from Ca to Ca2 plus, or plus 2. You can say it either way. Well, the answer is to go from calcium to calcium 2 plus, or plus 2, you're going to have to lose 2 electrons. So the atom gets smaller for calcium, right? So if you're on the left-hand side and you form the ion is smaller than the atom from which it was derived. So calcium would be bigger. Calcium's the bigger atom, or the bigger of the two between calcium and calcium ion. But let's take a look at bromine. Bromine's on the right side of the periodic table, and if you form bromine ion, what happens is when you add another electron to be like the next noble gas like krypton, you're going to make the ion bigger because you've added another electron above and beyond what you had before. So bromine ion this time would be bigger than bromine atom, right? Okay, hope that makes sense. Now let's turn our attention to electronegativities. Which has the higher electronegativity? Remember the trend. up and to the right. Electronegativities get higher. All right? Electronegativities get higher, but the noble gases don't have electronegativities. Let's compare chlorine and fluorine. Chlorine is number 17, fluorine is number 9. Fluorine is higher than chlorine, so fluorine would have the higher electronegativity. And don't forget, fluorine has the highest electronegativity of all the atoms on the periodic table. Now let's compare lithium atom and carbon atom. Lithium is number 3, carbon is number 6. They're both in the same period, but carbon is farther to the right, so carbon would have a higher electronegativity, a higher tendency to pull electrons towards it. How about beryllium and boron? Beryllium is number 4, boron number 5. Obviously, boron is farther to the right, so boron is going to have a higher electronegativity. Boron wins. And finally, let's do ionization energy. Chlorine or fluorine, which has the highest ionization energy? Remember, the first ionization energy trend is exactly the same as the trend for electronegativity. So fluorine is going to have a higher first ionization energy than is chlorine. It's going to be harder to remove that last electron from fluorine than chlorine. How about lithium and carbon? Lithium is number 3, carbon is number 6, carbon is more to the right. Carbon would have the higher electronegativity. And finally, beryllium versus barium. Beryllium is number 4, barium is number 56. So even though they're both in the same column, beryllium is higher, and therefore it would have a higher first ionization energy, just like that. Okay? One final point I want to make before we finish up this screencast is this. All the elements in a family or group have the same number of valence electrons. What do we mean by valence electrons? We mean the number of electrons in the last energy level, the last main energy level. All right? So I want you to look at the first column of your periodic table now, the one that includes hydrogen, lithium, sodium, potassium, rubidium, calcium, and francium. All of those have the same number of valence electrons. Now, I'm not saying they all have the same number of electrons. Hydrogen has 1 total, lithium has 3, sodium 11, potassium 19, and so forth. But all of them have 1 electron in the last main energy level. By the way, it's an S sublevel because it's in the S block, right? But 1 electron, and the fact that it has 1 electron, 1 valence electron means that everything in that family or group behaves similarly physically and chemically. Now look at the second family or group: beryllium, magnesium, calcium, strontium, barium, and radium. All those have 2 valence electrons in their outer shell, right? Their outer main energy level. 2 valence electrons, not 2 total, but 2 valence electrons. Now let's skip all the way across the transition metals, because the transition metals have tremendous variability in them. We can't really make a good prediction. But if we go all the way to the 13th column, the one with boron, aluminum, gallium, and so forth, we have 3 valence electrons. The next one, 4 valence electrons. The nitrogen group, 5 valence electrons. Oxygen has 6. Everything in that column has 6. Fluorine in its column has 7. And the noble gases have 8 valence electrons. Some people say it's 0 because none of them are available for bonding, and they define valence electrons as electrons available for bonding. But it's either 8 or 0 for that 18th column. All right? So there you have it. That tells us that the valence electrons are determining the physical and chemical characteristics as well as the bonding characteristics of elements. I'll see you in the next one. Thanks. Bye-bye.